Guys, is it too shiny on the board? I forgot that I can talk. Alrighty, guys. I see 8 of you are there. I know you guys all had different things going on, so hopefully people will watch the video at their convenience. Let me just wait a couple more minutes. I would start in about a couple minutes. Let me see if anybody else joins in. I'm just fueling up for the session, guys. Thanks, Sarah. So today we're going to review for Unit 4, Summative. And these have learning objectives 2.1 to 2.9, except for 2.2, which we will address later on. So the 3 major topics in this are states of matter, gases, and then solutions. So let's start with the focus on states of matter. This was an easier topic for many of you with a lot of prior knowledge. So solids, liquids, gases, as you progress from solids towards liquids towards gases, particle movement increases and intermolecular forces between them decrease. And gases practically have no intermolecular forces between them. As you convert solid to liquid to gas, you are increasing kinetic energy. And because of faster movement of particles, the intermolecular forces become weakened and they go farther and farther apart. If we were to plot a heating cooling curve where we measured time and amount of temperature, then what happens if you start with a really cool solid, which is below its freezing point? As you give it heat, its kinetic energy increases, so temperature increases. So it is solid here to here. At this point to this point, it is a mixture of solid and liquid. And the temperature does not change here because all of the heat given is used to overcome intermolecular forces of attraction. And that's increasing the potential energy. And because temperature is related to kinetic energy, you do not see an increase in temperature. So the given heat is used to overcome intermolecular forces or phase change. Then as you start heating it further, the liquids start converting into liquid's temperature steadily rises. I take it back, it doesn't convert yet. So this is all liquid still. And liquid's temperature steadily increases till it hits this substance's boiling point. And at that phase, you again see a flat line. And here you will have liquid plus gas combination all through this part. And then when it is turned all the way to gas, now you can increase its temperature again. Couple of things to notice here. Number 1, kinetic energy is directly proportional to temperature, but potential energy is not. So during phase changes, you do not see an increase in temperature given heat is used to overcome intermolecular forces of attraction. The other thing you must remember here, guys, is this second flat part in a phase change is showing vaporization. This part is showing fusion or melting. Vaporize for the same amount of matter, because you are observing this graph for the same sample of matter, the fusion requires lesser energy and vaporization requires a lot more energy, because in vaporization you are overcoming all the intermolecular forces of attraction, because gases have practically no intermolecular forces of attraction. But in this part, you are partly overcoming a few intermolecular forces, because solids have a lot more than liquid, but liquids still have significant number of intermolecular forces of attraction. And that is why heat supplied in this part for liquid to gas conversion is greater than heat applied in this part. And that is as much as in detail we went over on states of matter. Basically, particulate level drawings, kinetic to potential energy conversions with phase changes, and that's where our focus was. Now, I open the time now for you to ask me questions on states of matter from the practice problems. The practice quiz we will do after we are done going over each of these three. But if you have questions from practice problems on Unit 4, I'm happy to go over it. And they will be questions 1 through 8. So any questions on 1 through 8 on practice problems, I can address now. I'm assuming this is the easier concept, so I'm not seeing any questions. Do you guys need a little bit more time to think about it, or are you good with this topic? Number 6, Sangeeta asks. Number 6 says, which of the following does not occur when liquid water freezes to form ice? So we are talking freezing process where liquid is converting to ice. Potential energy changes. We know that changes because more bonds are being formed. So the particles are coming closer. So attraction is increasing, potential energy is increasing. A is not an option. B, temperature stays the same. That definitely occurs. So that is not an option. The cooling curve for the change is flat. That is true as well, because during this time, the heat is being removed. That is causing the attractions to form. So we are talking again about potential energy. So C is correct. D says the average kinetic energy of particle changes, and that is not true. It doesn't happen during any phase change, because during any phase change, all the heat is used up to overcome intermolecular forces of attraction. That is why number C's answer is D. There's no change in kinetic energy during phase change. And number 3. What of the following is not true? When water vapor at 100 degrees condenses to liquid, the phase change releases large amount of heat. That is true, because from gas to liquid, particles are coming closer, right? So the extra energy has to be released. You're welcome, Sangeeta. B says liquid water at 100 degrees causes more severe burn than water vapor at 100 degrees. That is not true. Because, so B is not true in this case, guys, because water vapor will cause more severe burn, because vapor will first condense to liquid, so it will give off all of that heat, and then that liquid at 100 degrees will convert to your room temperature, so then it will give off more heat. So B actually is not true. C is when water vapor at 100 degrees condenses to liquid, the phase change absorbs large amount of heat. That is not true either. So B and C are both not true. So the answer is D. I think this answer was initially wrong in my key, but I fixed it. So the correct answer for this question is D. So that is number 3. Number 6. Which of the following does not occur when liquid water freezes to form ice? We know that potential energy will change, so A is not an option. The temperature stays the same, that is true. The cooling curve for the change is flat, that is true. The average kinetic energy of particle changes, that is not true, because during phase change, all of the heat is used to overcome intermolecular forces of attraction, and which is related to potential energy. So during phase changes, there is no kinetic energy change. Hence, for 6, answer is D. You're welcome, Dan. And 3, why is B true for number 3? Manju, B is true because you have 100 degrees steam, right? So how does it happen? So 100 degrees water in liquid state will need to turn to 100 degrees steam. And let's say if our water is at 25 degrees Celsius, which is room temperature, our body temperature is a little bit, I don't know, it is about around 99 Fahrenheit, right? Or 98.6 Fahrenheit. So whatever. So let's say it is at 25 degrees, that is the room temperature. So if you think about a water in liquid state at 25 degrees, first you need to give it heat to change its temperature to 100. Then you need to give it heat to separate the water molecules. Let's say these are water molecules, right, at 25 degrees. At 100 degrees, it is the same water molecules, right, maybe a little farther apart, little higher kinetic energy. But at 100 degrees, these molecules are really, really far apart, right? So you are also adding energy to remove them. Now think of its reverse. If you have 100 degrees vapor, first it'll need to give off energy to bring these particles together. So what you will get is 100 degrees of water. Then you will get 25 degrees of water, a little bit closer, a little less kinetic energy, right? So this part, 100 degrees water to 100 degrees steam, is what results in loss of lot of heat on your skin surface. So burning from a steam is definitely a lot more heat than getting burned from 100 degrees water. Okay, Talia says, why does the answer for 8 not include E or F? 8. The graph below, number 8, the graph below represents the uniform heating of a substance starting at melting point when the substance is solid. Which segment increases shows, so it is AB and CD and EF. But is there an option with all 3? No. So it's AB and CD. And in all other options, there is a flat portion involved, right? Am I correct in that? Yes. So the only option where there is no flat portion is A, because if we are talking about kinetic energy increases, then we need to look at the ones where there is a non-flat portion. So A will be an option here. Did you get that, Talia? You're welcome, Manju. So EF does increase in kinetic energy, but it is not shown here in the option. If it were, it will be treated as increase in kinetic energy. That is correct, Talia. So number 3 is done. We are number 2 for Sarah. Number 2 says, the cooling curve for a pure substances as it changes from liquid to a solid is shown above. The solid and liquid coexist. So here you are cooling it. So this is liquid and you cool it and then it turned to solid. All the points between Q and S. So both liquid and solid are present between Q and S, or you could have written R and S if they gave you option like that, because this is where in the flat part is where there is equilibrium between the liquid and solid states. That is why. You got it, Sarah? All right. Okay, let's move on to the second part of this. And the second part of this deals with gases. And as we talked about gases, remember we first talked about KMT, or kinetic molecular theory. And KMT gives us a theoretical basis for explaining very many of gases' peculiar properties, such as expansion or compression and obedience to gas laws. All of those experimental observation or day-to-day observation can be explained by the theoretical model given by KMT. What is KMT model? It says the gas particles are so small that the volume of the gas particles as compared to overall gas volume is negligible. Hence, gas is mostly empty space. And if gas is mostly empty space, then what's going to happen is you can compress it a lot. It's highly compressible. The second postulate is no gas volume. The second postulate is that negligible IMFs, intermolecular forces between particles. So gas particles really can go far apart from each other. The intermolecular forces between them are pretty much non-existent. And that explains why gases can expand. If you pop a balloon, the gas goes everywhere, right? So the expansion of the gases is because of negligible intermolecular forces. The next thing this theory says is gas particles are in constant rapid random motion and they keep going straight till they hit each other. And if two gas particles collide with each other, it results in an elastic collision, meaning there is no net loss of energy. Energy can be redistributed, but it is not lost. So elastic collisions. The next postulate of KMT says that the gas pressure is generated when the gas particles hit or collide with the wall of container. And every time a gas particle collides with the wall of container, it exerts a force. And this force per unit area is called pressure. So pressure is generated when the gas particles hit the wall of the container, not when they hit each other. And the more is the force per collision, or more are the number of collision, the more is the gas's pressure. And the last postulate here says that the average kinetic energy of a gas sample is directly proportional to the absolute temperature of the gas. So higher the temperature, the more will be the average kinetic energy. And its application is if I have two gases like hydrogen and nitrogen, both at room temperature, they will have same average kinetic energy. Note I'm saying average. The average will be the same, right? But the average molecular speed will not be the same. The lighter gas will have higher average speed because kinetic energy is half mv squared. So if the product is the same, then the one with the lesser mass has to be moving faster to get the same product. Okay, so this was KMT theory. However, this all assumes ideal behavior of gases. Okay, but the real gases do not behave ideally. Real gases' behavior is different than ideal gases. Real gases do not obey all gas laws at all temperature and pressure conditions. And the reason for that is twofold. Number one, we have assumed that gas particle volume is negligible. But in reality, the gas particles have some volume. And what that does is think of it like that. So we had assumed in our initial model that gas particles have negligible volume, right? Now, if gas particles do have some volume, then the overall gas volume, real gas volume, is larger. So to make the gas volume, real gas volume, look more like ideal, you subtract subtract from volume a factor. What factor? I'll tell you in a minute. Similarly, our second postulate was there's no intermolecular forces between gas particles, and that's again faulty. There is some intermolecular forces that exist between gases. And what happens when a particle is moving to collide with the wall of the container? If another particle is attracting it, then this force gets minimized. It doesn't hit with the same force. As a result, the pressure of real gases is lower than ideal. And to make up for this, we add a factor to pressure. And that leads us to ideal gas equation. Ideal gas equation comes out of combining four laws: Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. And this equation looks like PV is equal to nRT. And ideal gases are the ones that obey gas laws under all pressure and temperature conditions. But we know that the real gases obey it best at low pressure and high temperature. Deviation from ideal behavior is the greatest at high pressure and low temperature. And this ideal gas law can be written three different ways. D is equal to PM over RT. And today we did a lab on it. Molar mass is MRT over PV, right? I think that was it. I can derive it, but I think that was it. So these are three different versions of ideal gas law. To modify it to fit with the real gases, it is P plus N squared A over V. V minus NB is equal to nRT. It's called van der Waals equation. This equation has a correction factor to add to the pressure so that the effect of non-negligible intermolecular forces can be added in there, and a factor is subtracted from volume, so the effect of non-negligible particle volume can be accommodated in real gas equation. So this much was the theoretical part. R's value here is 0.0821 liter atmosphere per Kelvin mole. And one more thing here is gas stoichiometry. I have a little bit room here. I'm going to sit here. So gas stoichiometry is ideal behavior at STP and non-STP. At STP, we use the relationship 22.4 liter is the volume that's occupied by 1 mole of any gas. Non-STP, we use Pavnert equation. Gas stoichiometry typically is used when you are given some amount of gas that was collected and you're asked the volume or mass, either the volume of another gas or mass of a solid. And I will do one problem with you on gas stoichiometry so you can see how that plays out. But I would like, before I do gas stoichiometry, are there any questions on the theoretical part of gases? I am open to answering your questions on the theoretical part of gases. Not the numerical part yet, but on theoretical concepts. Do you have any questions from the practice handout? So those will be questions 9 through 12. Number 12, yes, definitely. So number 12, I'm going to erase this. Oh, shoot. My laptop is running out of battery. Give me a second, elements, to plug in my charger. Let me see if my charger will reach that far. Okay. Oh, I will have to change the angle of this. Can you still see the board behind you guys? I know the angle has changed. Is that still okay? Can you confirm that, please? Because my charger wouldn't reach this far. Okay, I will not go very far down. Okay. Okay. Let me know if I go out of field of view. Okay. So you wanted me to draw out number 12. Number 12 says draw a particulate level drawing of the changes that will be observed in a sample of oxygen when the temperature is increased from 40 to 150 at constant pressure of 1 atm. So, and they have given you a legend as oxygen as this. You can choose to draw any number of particles, but 4 to 6 is a good number of particles, right? So let's say this is at 40 Kelvin and this is at 150 Kelvin. So let's say we took 1, 2, 3, 4 particles. So what you will show at 150K, 1 atm, when I say guys, I mean the external pressure. So the volume remains the same. Maybe that's a clarification I needed to do, that the external pressure is 1 atm, not the gas pressure. Okay, so the volume is here. So you're maintaining that. And what will happen as the pressure inside increases, the volume will expand, right? So here, what you will show is still 4 of those, but I'll show faster movement. Okay, and you might have to specify this, that the movement is faster. Now, on to number 9. Number 9 says, NO2 is one of the greenhouse gases responsible for brown color of the smog. 2 nitrogen dioxide molecules can react to form 1 nitrogen tetroxide. Draw particulate level drawing showing 2 molecules, each of NO2 and N2O4 above a liquid solution of N2O4. Okay, so here what we need to do in number 9 is we need to make a liquid solution of N2O4. So you can use legend, whatever you decide to. So let's say I make N2O4 like that, right? N2O4, N2O4. You can use any, right? N2O4. It's liquid, so they're fairly closer together. N2O4, okay. And then NO2, right? So above this surface, I want to show it is not worded very nicely. I should change the wording, showing 2 molecules each of NO2 and N2O4 above a liquid solution. So it should be just 2 molecules of NO2 because I don't think, they say 2 each, you can. So this was N2, right? NO2. NO2, N2O4, N2O4. So basically the question here is trying to see that you can draw the liquid particles closer together, right? And as you draw them in the gas, you draw them above the liquid surface and a little farther apart is what they will look for. So that'll be number 9. And Sarah, is that you who wants number 6? Can you please confirm? Number 16. Who wants number 16? Can you please type your name? Okay, so I don't recognize. It's in a language, guys, that I don't understand. So would number 16 please introduce yourself so I can do your problem? Who's number 16? Ashley, no problem, Ashley. Okay, Ashley, so number 16. Okay, we'll get to 16 in a minute, Ashley. That's the numerical part of gases, okay? But let me ask everybody, are there any other question on the theoretical part, the non-calculator section till about 12? And then I do want to do a stoichiometry, a gas stoichiometry question, and then I'll take the questions from here. But I do want to do one gas stoichiometry question. Okay, so let's move on to a gas stoichiometry question. And remember, when you're given a gas stoichiometry question, the biggest thing you're trying to identify even before you start doing the question, is it a STP problem or is it a non-STP problem? Because if it is a STP problem, then it's 22.4 liters to 1 mole. But if it is non-STP, then we use Pavnert equation. Okay, so we need to determine that early on as we are reading. So here is a sample problem for you, which includes collection of gas over water and gas stoichiometry. This is the most challenging kind of AP problem, so I'm doing one of those, and my hope is you can then do the simpler ones. So the question says 193 milliliters of oxygen was collected over water when the atmospheric pressure was 762 millimeter mercury. The vapor pressure of water is collected at 23 degrees Celsius over water. The vapor pressure of water at 23 degrees Celsius is 21.1 millimeter mercury. And this question has 2 parts. And then they give you the equation. 2 KClO3 solid gives you 2 KCl plus 3 O2 gas. That's the equation. Now, there are 2 parts to this question. The first part says, how many grams of KClO3 solid were used to produce this oxygen? That's the first problem. The second one is, in lab, another impure sample of KClO3 was found to produce 185 milliliter of oxygen under the same conditions of temperature and pressure. What is the percent purity of this sample? Assume that I'm going to take a break. That's my daughter. I'll be right back. Hey, happy birthday. Okay, it's recorded. I'll be right back. That's just lovely. Okay, I need like half an hour, 15 minutes more. I'll be right back. This all gets recorded. Okay. Sorry, guys. Okay. So, coming back here, assume that the first sample is 100% pure. Okay, so if we analyze this problem, there are two parts to it. And in first part, they collected the gas, oxygen over water, and using the data from here, they want us to get the grams of KClO3. We know when we collect gas over water, we got to subtract the vapor pressure of water from there. And then using the moles, you can get moles of this from there. Okay? All right. So let's do. Hey, guys. Can you go inside the room? Papa, I'm recording this. Under. Yeah, thank you. All right. Yeah, my family is all around. So I need to do this fast, guys. Okay. So here, now what we do is using, can you see green? Maybe not that well. Maybe I should do the blue just to separate the process from here. So we will be using, first of all, we know P of oxygen is P ATM minus P water. We got to subtract the water vapor pressure. So total pressure is 762 millimeter mercury. And we subtract from here 21.1 millimeter mercury. And when we do that, we get 740.9 millimeter mercury. That is the pressure of oxygen gas, or that is 0.975 ATM. I like to do my problems in ATM, guys, and I don't need to worry about the R. Okay. Now, we will be using PubNet. N of O2 is P of O2 V over RT. Pressure of oxygen is 0.975 ATM. Volume is 0.193 liters. R is 0.0821 liter atmosphere per Kelvin mole, and temperature was 296 Kelvin when you add 23 to 273, and you get 0.00774 moles of O2, but we don't need to find O2, right? What we need to find is moles of KClO3. So I'm going to write here 0.00774 moles of O2. 3 moles of O2 make 2 moles of KClO3, and 1 mole of KClO3. I don't know the molar mass, guys. I put it in calculator. So when you do molar mass of KClO3, you get, your answer is 0.632 grams of KClO3. So this is a classic gas stoichiometry problem where you have collected some gas over water, and using the gas moles, you're trying to figure out the solid moles using mole ratio. But before you can use mole ratio, you need to know the moles of the gas, and you know the moles of the gas using Pavnert equation. So that is part one of this problem. Any questions on part one of this problem? Are we good? Okay, let's do the part two of the problem. And in part two of the problem, and I just kind of wrote it up thinking that this kind of problem can be made. So in part two of the problem, what we will do, the thought process is, now we'll use 185 mils, and using P ATM minus P water, we get P of O2, and then we get moles of O2, and from here we get moles of KClO3. From there we get grams of KClO3, right? And we know that we should specify the amount of KClO3 here. So let's say another sample of 0.63 grams. They need to give us the amount of KClO3. So we know experimentally we got these many grams, and we'll divide it by 0.63 grams of KClO3, and we will times it 100. I kind of wrote this, guys, so some of the numbers may not add up, but I wanted to show you another angle here, that this kind of data could be used for percent purity as well, where they give you two samples. In one, you're not generating the optimal amount of gas because there's impurity, and you can get moles of gas and then figure out the percent purity too. I haven't seen a problem like that asked, but I thought, why not? So really our focus is on part one, but this kind of problem can also be used to calculate the percent purity. Okay, so now guys, I ask you if you have any questions on gas stoichiometry. That would be problems 13 through 17. Or 13 through 22. So anything on 13 through 22 that you want me to go over. Problems 13 through 22. Oh, Sarah had asked, or somebody had asked, 16. Okay, let me do 16 now. So problem number 16 says the density of liquid nitrogen is 0.808 grams per ml. And they are asking what volume at STP must be liquefied to make 10 liters of liquid nitrogen. So we're going to convert this 10 liters of liquid nitrogen to grams using density. So from volume, using density, we get grams, then we get moles, and then we use STP relationship. Okay, so 10 liters nitrogen, okay, 1000 or 10 power negative 3 liters. 1 mil is 10 power negative 3 liters is 0.808 grams, right? And you will get 8.08 times 10 power 3 grams, and you divide it by 28 grams per mole, and you will get number of moles of nitrogen, right? And you know that 1 mole of nitrogen is 22.4 liters nitrogen at STP. So if you have your, I have my calculator. Let me see if it works. Yes, it does work.
Which scale like in load or
8080 divided by 28 is 288. 288.57, and then that times 22.4 is 6464, or 6.464 times 10 power 3 liters. 6 point, yeah, somewhere there. Number 17 and 21. So number 17 is, there are 3 1-liter flasks at 25 degrees and 1013 kilopascal, and they ask which flask contain 0.041 moles of gas. So you calculate moles is PV over RT. All of the flask have 1013 kilopascal, right? And 101 kilopascal is 1 atm, right? 1.01 times 10 power 5 pascal, 5.2. I think this conversion is right, guys. You want to double check. And then volume is 1 liter. R is 0.0821 liter atmosphere per Kelvin mole, and temperature is 25 plus 273 Kelvin, and that gets you 0.041 moles of gas. And this will be the same for all the 3 gases, because pressure, volume, R, and temperature are the same in all. That is why none of these are true, because they are asking, oh, I think you get 0.41. Sorry, guys, not 0.041. You get 0.41, and they ask you which one has 0.041 moles of gas. So your answer is none of them, because they all have 0.41. All right, Sunny and Sarah, number 17 is good. And I will do number 21 in a minute. You are welcome. So number 21. A rigid 5-liter container contains 24.5 grams of N2 and 28 grams of O2. Okay, calculate the total pressure. So P total will be N total RT over V. So you can do it one or the other way. You can get the pressure of nitrogen using PV is equal to nRT and get the pressure of oxygen, or you can find the total moles, because it doesn't matter which gases moles are there. As long as you have the total moles, you add them up and do RT over V. So the total moles will be 24.5 grams divided by 28 for nitrogen, plus 28 divided by 32 for oxygen. And then R is 0.0821 liter atmosphere per Kelvin mole. Temperature is 298 and volume is 5 liters. When you solve it, then you should get 8.56 atm. Then for part B of it, the temperature is decreased to 280. Now, what is the mole fraction of nitrogen? Mole fraction is represented by X. of nitrogen means moles of nitrogen over total moles. So how many moles of nitrogen we have? 24.5 divided by 28 grams per mole. And total moles will be 24.5 divided by 28 plus 28 grams over 32 grams, right? And this will give you mole fraction of 0.500. And mole fraction does not have a unit because it's a ratio. Then part C asks, oh, there is I and II. II says the partial pressure of nitrogen will be how much? Partial pressure of nitrogen will be moles of nitrogen RT over V. And you get moles of nitrogen from here. You know R, you know T, you know. Oh, your T has changed now, right? So your T is now 280. It was different T there. So you put these moles because moles won't change with temperature, right? It is like a matter. R is the same, but T has changed to 280 and volume is still 5 because it's a rigid container. So you put those moles, R will be 0.0821 liter atmosphere per Kelvin mole. T will be 280 now. And V will still be 5 liters. And then you will get 4.62 ATM, I think around there. And part C says that if there is a pinhole size leak, then will the ratio of nitrogen to oxygen increase, decrease, or the same? Remember, the heavier gases diffuse slower and the lighter gases diffuse faster. So nitrogen's molar mass is 28, oxygen is 32. So nitrogen will go faster. So the numerator will decrease. So the ratio will decrease because nitrogen will effuse faster. So that was number 21. Number 18. So number 18 is a gaseous mixture of oxygen and krypton have a density of this. What is the mole percent? So for that, you have to get the molar mass of the total mixture will be dRT over P. Density is 1.104 grams per liter. R is 0.0821 liter atmosphere per Kelvin mole. Temperature is 300 Kelvin. And the total pressure here is 435 millimeter mercury over 760 ATM. And when you do that, you get the total molar mass to be 47.5 grams per mole. And you know this is coming from both of them. So let X be oxygen. So how much would the krypton be? Krypton will be, if the whole thing is 1, so it will be 1 minus X. Remember, we've done this in previous problems. You assume 1 to be X, and because both of them, the whole fraction is 1, so other becomes 1 minus X. This equal to X times 32, because we took oxygen to be X, plus 1 minus X times molar mass of krypton, which is 83.5 grams per mole. And when you do that, then X comes out to be 0.701 if it is out of 1. If it is out of 100, it'll be 70.1%. So that is number 18. 19C. 19C. Calculate the ratio of average speed of hydrogen to water vapor. Okay, so 19C, ratio of rates of hydrogen to water will be square root of molar mass of water to molar mass of hydrogen. This is one of the equations in your equation sheet. So when you square root of water, water is 18, hydrogen is 2, so 1 and 9, so it is 3 to 1 ratio. You just plug in the molar masses in the formula for 19C. Mole ratio in 21, Dan. So if you have 24.5 grams of nitrogen, how many moles of nitrogen you have? 28 grams nitrogen is 1 mole nitrogen. So that is how many moles? 24.5 divided by 28, you have 0.875 moles of nitrogen. And how many moles of 28 grams of oxygen? And 1 mole oxygen is 32 grams oxygen. So 28 divided by 32 is 0.875 as well. So if you look at the ratio of 1, it is 0.875 over 0.875 plus 0.875. So if without doing calculation, I think logically it's 50 and 50%. So mole ratio is 0.5. Mole fraction is moles of 1 over total moles. So mole fraction is 0.5. N2, what is N2? Chilina, I'm not sure I get your comment. Can you clarify for me, Chilina?
But there are some Diwali celebrations.
All right, perfect. So I think it's getting closer to 5. Now I'm going to quickly address the solutions. So I went over the 3 steps of a dissolution process and molarity. Molarity we've done a lot, so I think I'm going to skip that unless you have any questions on the solution. Then I'm going to take 10 minutes to answer questions on practice quiz. So do you have any questions on Unit 4, practice sheet 24 through 31? Anything 24 through 31? (23B). 23B. In the 10 more minutes, okay? 23B. Indicate whether the number of CO2 molecules is greater than, equal to, or less than CO. So you will look for just the pressure, right? If they're at the same temperature, CO has 2 atm pressure and CO2 has 1 atm pressure. So there is more CO. Okay. 24. Label solute-solvent interactions. So guys, can you see here? So basically, you have the ions there, and between the solid ions, right, there'll be interaction as ion-ion. Between water molecules around it, there will be interactions there. And when you dissolve it, what happens? Around the cation, water molecules go there. Their oxygen end pointing, and around the anion, the hydrogen end is pointing. And pretty much this is the concept. This is what I was looking to see. Solute-solute and solute-solvent interactions. Karina, practice quiz, I got 0.003 moles, and bit off is okay, as long as it is not because you missed to subtract the water vapor pressure, it's okay. 24 BC. So guys, clarify, right? It's wasted effort. 24B, step particulate level drawing. The step 1 is you'll have to separate the solute particles. Step 2 will be you have to separate the solvent particles. Refer to the board notes that I had done on the board. And step 3 will be mixing these separated particles. So the drawing that was made there, they had Cl minus and they had water molecules around it and K plus. So I was hoping that you'll be able to identify some K plus with water molecules around it, and you'll be able to identify some Cl minus with water molecules around it. So then you could label it solute-solvent interactions, right? This is solvent, this is solute, this is solute, this is solvent. So these could be solute-solvent interactions. And if you had some solid KCl in there, then these interactions will be solute-solute interactions. But if you had some water in there, it'll be solvent-solvent interaction. And then see, why are some dissociation exothermic? Why are some endothermic? Guys, I showed you supersaturated solution, remember? And that was hot. And you answered to me, why was that exothermic? Because solute and solvent like each other. Why are some endothermic? Because solute and solvent do not have high affinity for each other. Okay, Talia? And now Sunny wants 28. What is the volume? So I'm going to tell you the methodology for 28. Molarity is moles per liter solution. You are given molarity. You will use grams of calcium nitrate to get the moles, and then you can calculate liter of solution. Okay, so for calcium nitrate, if you have 45 grams of this, you divide it by molar mass of calcium nitrate, that will be moles of calcium nitrate. Okay, so that was 28. Now I am moving on to the practice quiz. We are at 5:02. I can take 5 more minutes, guys. Any questions on the practice quiz that you did not get? Those of you who have not taken the practice quiz, you want to leave the video session right now and come back to it once you are done doing your practice test or practice quiz. Which question, Sunny? Number 28? Is it how much? Okay, let's do it together. What is the molar mass, Sunny? You're getting, type it real fast. What's the molar mass, Sunny, of calcium nitrate? Oh, a couple of you are getting that, okay? So what I have here is the molar mass is 164 grams. Is that what you're getting? Okay, perfect. Now, molarity will be moles. And how many moles is it? If you divide 45 by 164, how many moles are you getting? I show 0.274 in my calculations. A student told me this, so I actually have a whiteout on this. So I did that. Is that not right, guys? So Sunny and Chelina just confirmed the moles. I think there might be a problem with that. I show a whiteout on this, so I changed it. I wonder if a couple of students told me or... But this is the method. And Karina, number 2 on second page. On what, Karina? Number 2 on second page of what? Practice quiz? Number 2 is on the first page of practice quiz. Oh, can't see the board. Okay, let me write over here. Okay. So molar mass is 164 grams and 45 divided by 164 grams is how much? Yes. 0.274 divided by 1.3 liters is equal to 1.3 molarity is equal to liters. 0.211, yeah, so it is 210. It is 210, guys, okay? 2.4 to 2.6. .3. Okay, number 2. Okay, so number 2, and I think this is my last question, guys. I think I'm way over my time. Oh, goodness. Okay. Can someone help here while you guys are waiting? Okay, for practice test, go over 3BC and 2.2. So can someone help Sarah? And I am working on Karina's problem. Okay, so Karina's problem is 2.46, number 2. There is 2K plus 2H2O gives you 2K plus 2OH minus plus H2. And they say 0.4 moles of potassium. That means 0.2 moles of hydrogen using mole ratio. And you know 1 mole of hydrogen is 22.4 liters hydrogen, and you get 4.48 liters. Oh, sorry, hydrogen. Is it hydrogen? Yes, hydrogen. So you know it is at STP, so you know it will be 22.4 liters. So the thought process is from moles of K, you get moles of hydrogen and then convert it to volume. Okay, Sarah, 3B and C. 3B, calculate the percent yield. And Sarah, can you specifically ask what was the problem in 3B? Is it the formula? Is it calculation? Or you're not getting the answer? So 3B, I'm just going to go ahead. The formula of percent yield, okay? So percent yield is experimental yield over theoretical yield times 100. Experimental is what they give or you make out of experiment. This is what you calculate based upon the formula. So here, experimental, you will get from part A. Whatever you calculated there, that is your experimental. And theoretical is given to you. Or you calculate using the formula how much theoretically you should get. So theoretical yield you get from converting 0.200 grams of C2H5OH converted to moles, then use mole ratio and get moles of C2H4 because they've given you the equation, and using this mole of C2H4 here and the one that you got in part A, moles of C2H4 there, you get percent yield. Percent yield, you can use either the moles or the grams. In this case, we can use moles because we can calculate moles easier. And part C, when you are drawing for 3C, I am using the legend. This has water and this has CH4. So in the box, I will have both of those. The ratio doesn't matter. And water molecules. As long as you have drawn both water molecules and CH4 in there, that is good. And 2.2 I just did for Karina. So where did 0.2 moles of hydrogen come from? From this mole ratio. What is the mole ratio between potassium and hydrogen? 2 to 1. So if we have 0.4 of this, we will have half of that or 0.2 of that. All right, guys. I hope that was helpful. I think I'm going to call it a day here. There are very many things to do. Oh, thank you so much. I appreciate that, Talia. That is very thoughtful of you. Yeah, they've been waiting. My daughter just drove from Berkeley, so now I can get to hang out with her. Thank you so much, everybody. You guys are very kind. I appreciate that. Thank you. And I will upload the video on Facebook group soon. Okay. Bye, guys. You'll be fine tomorrow. Okay. Bye.